Hello viewers, in today's session we are going to discuss yet another important and very conceptual problem from limits involving the greatest integer function, right? So here we have to evaluate this limit, that is limit x tends to 2 minus. Here the negative sign shows that we have to find the left hand limit of this function, which is e raised to 100th power of greatest integer of x plus 2 divided by 4, right? So here we'll evaluate this limit with the help of some important properties of greatest integer function, right? So let us call this limit as L, right? So here x approaches to 2 from the left of x is equal to 2, right? So here we have x is equal to 2 and we have to find the left hand limit. So when we approach x is equal to 2 from the left of x is equal to 2, we are in the neighborhood of x is equal to 2, and this point is 2 minus h, where h is a positive quantity and it is infinitesimally very small, right? And h is very small and it lies between 0 and 1, right? So what we will do here, we'll convert this limit in terms of h by substituting x is equal to 2 minus h, so that when x tends to 2, h tends to 0, right? So now this limit takes the form that is L limit h tends to 0, and remember here we have the greatest integer function two times, right? So here first we have the greatest integer of x plus 2, then we have the greatest integer of this entire term, right? And then we have the exponent 100. So here we have e raised to, then here we have the greatest integer function raised to 100, and then we have greatest integer of x plus 2. So x can be taken as 2 minus h. So here we have 2 minus h, then we have plus 2, and then here we have 4, right? Okay, so now we can write it limit h tends to 0 e raised to greatest integer. Here we have 100. This is 2 plus 2, 4. So we have greatest integer of 4 minus h divided by 4. So the first property is greatest integer of x plus m is equal to m plus greatest integer of x, where this m belongs to the set of integers, right? So m belongs to the set of integers, and here this x is a real number, right? So greatest integer of x plus m is m plus greatest integer of x for all x belonging to the set of real numbers. So now we can rewrite this term, that is greatest integer of 4 minus h, as greatest integer of 4 plus minus h, and we can take this 4 as m. So we can now write here 4 plus greatest integer of minus h, right? So now greatest integer of 4 minus h divided by 4 can be written as 4 plus greatest integer of minus h divided by 4, right? And now we can separate these two terms by writing 4 over 4 and 4 over greatest integer of minus h. So we have 1 plus greatest integer of minus h over 4, right? So now this limit L, it takes the form limit h tends to 0. We have e raised to greatest integer raised to 100, and for this term we can write 1 plus greatest integer of minus h divided by 4. So now we know that h, it lies between 0 and 1, right? So h lies between 0 and 1. So if we multiply throughout by minus 1, then we have 0 and the direction of the inequality get reversed. So here we have minus h, then here we have minus of 1, right? And we can also rewrite this inequality as minus 1, then here we have minus h, then we have 0, right? So when h lies between 0 and 1, then minus h lies between minus 1 and 0. So the greatest integer of minus h should be equal to minus 1. So we can now take greatest integer of minus h as minus 1. So now this limit L is equal to limit h tends to 0. We have e raised to greatest integer of 1, and then plus, here we have plus sign, then we have minus 1 over 4 raised to 100. So now we can remove this limit notation because here we do not have h. So now we can write simply e raised to greatest integer of 1 minus 1 over 4. So this is 4 minus 1 by 4, that is 3 over 4, right? So we have greatest integer of 3 over 4 raised to 100. And we know that the greatest integer of 3 over 4 is 0, because 3 over 4 is 0 0.7. This is 4 sevens are 28, then we have 5 here, right? So this is 0. So here we have e raised to 0 raised to 100, and this term is 0. So we have now e raised to 0, that is equal to 1, right? So the limit of this function is equal to 1 when x approaches to 2 from the left of x is equal to 2. Hello viewers. In today's session, we are going to discuss a very important and conceptual problem from limits, right? And here we are going to discuss this limit involving the greatest integer function, right? So here we have to see whether the limit of this function, that is x raised to greatest integer of x over 2, when x tends to 4, it exists or not, right? So for the existence of limit of a function at a particular point, what we do, we find out the right hand limit and the left hand limit of the function at the given point, and then we see whether the right hand limit exists and it is finite, or the left hand limit it exists and finite, and the right hand limit must be equal to the left hand limit for the existence of the limit of a function at a given point, right? So let us start. So let us first find out the left hand limit of this function when x approaches to 4, right? So here we have x is equal to 4, and when we approach from the left of x is equal to 4, then we have a point in the left neighborhood of x is equal to 4, such that this point may be taken as 4 minus h, right? And when we approach x is equal to 4 from the right of x is equal to 4, then we have another point in the right neighborhood of x is equal to 4, such that this point is the 4 plus h, right? And where this quantity h is infinitesimally very small, but h is a positive quantity lying between 0 and 1, right? So the left hand limit of this function may be written as limit x tends to 4. We put a negative sign over 4, and here we have f of x, right? Okay, so now when we approach x is equal to 4 from the left of x is equal to 4, we have x is equal to 4 minus h. And when x tends to 4, then obviously h tends to 0. So now writing the left hand limit in terms of h, we have limit, then we have h tends to 0. Now for x tends to 4, we have h tends to 0, and here we have x is equal to 4 minus h, right? Okay, so now we have limit h tends to 0, and f of 4 minus h may be written by replacing x by 4 minus h, right? So we have 4 minus h raised to the greatest integer of 4 minus h over 2, right? Okay, so now we have to concentrate on this term, that is greatest integer of 4 minus h over 2, and we'll solve this expression by using an important property of greatest integer function. And the property goes like this: if we have greatest integer of x plus p, where this p is an integer, then greatest integer of x plus p can be written as p plus greatest integer of x, where x is some real number, right? So this is an important property of greatest integer function, which is very useful in solving many problems. So now we can write greatest integer of 4 minus h over 2 as 4 over 2, uh, distributing this 2 over 4 and h. Here we have minus h over 2, and now we have 2 plus, and now we can write bracket minus h over 2, and here we have the greatest integer function, right? So now this term is of this form, because we can write it like this also: minus h over 2 plus 2, right? Okay, so now our p is 2, and our x is minus h over 2, because this 2 obviously belongs to the set of natural the integers, and here x is minus h over 2, and this belongs to the set of real numbers, right? So we can now write this expression as 2 plus greatest integer of minus h over 2, right? Okay, now see here, h lies between 0 and 1. So if we multiply this inequality throughout by negative 1, we have minus 0, that is simply 0, and the direction of the inequality get reversed. So we have minus h, here we have minus 1. So rewriting this inequality as minus 1 less than minus h, then here we have 0. So now if we divide both sides by 2, we have minus half and minus h over 2, and here we have 0. So this inequality suggests that this minus h over 2, it lies between minus half and 0. So here we have minus 1, here we have 0. So minus h by 2, it lies between minus half, we have minus half somewhere over here, and minus h by 2 lies between minus 1 and 0. So the greatest integer of minus h by 2 should be equal to minus 1 by definition of greatest integer function, right? So minus h by 2, it lies between minus half and 0. So the greatest integer of minus h by 2 should be equal to minus 1. So here we have 2, and then here we have minus 1. So this is 2 minus 1, that is 1, right? So now this limit goes like this: limit h tends to 0. Here we have 4 minus h, and here this term is now equal to 1. So here we have 1. So now we can take h is equal to 0 here. So we have 4 minus 0 raised to 1, that is 4 raised to 1, that is 4, right? So the left hand limit of this function when x approaches to 4 is 4. Now let us find out the right hand limit. So the notation for right hand limit is the limit, and here we have x tends to 4. Here we write a positive sign, and here we have f of x. So now when we find out the right hand limit, we are approaching from the right of x is equal to 4. So here we have the point 4 plus h. So we'll write x is equal to 4 plus h, and when x tends to 4, then h tends to 0, right? So now the right hand limit can be written as limit h tends to 0, and we have f of 4 plus h. So this is now limit h tends to 0, f of 4 plus h can be obtained by replacing x by 4 plus h. So we have 4 plus h raised to greatest integer of 4 plus h over 2, right? So now we have to concentrate on this term, that is greatest integer of 4 plus h over 2. So as we have done in this case, we'll follow the same steps here. So we have greatest integer of 4 by 2 plus h by 2. Then we have 2 plus h over 2. And now the value of p is 2, and x is h over 2. So we can now write 2 plus greatest integer of h over 2. Now see, the value of greatest integer of h over 2 is equal to 0, because h lies between 0 and 1. So h over 2 should be, it should lie between 0 and half. So the greatest integer of h by 2 is 0. So here we have this term equal to 0. So now we can write 2 plus 0, that is equal to 2, right? So now this limit can be written as limit h tends to 0, and here we have 4 plus h and raised to greatest integer of 4 plus h over 2, which is equal to 2. So here we have simply 2. So now we can take here h equal to 0. So we have 4 plus 0 raised to 2. So this is 4 square, that is 16, right? So the right hand limit is equal to 16, and the left hand limit is equal to 4. Now see, here the right hand limit and left hand limit both exist, and both are finite, but they are not equal to each other. So the right hand limit is not equal to left hand limit. So we can safely claim that this limit, that is limit x tends to 4, f of x, where f of x is x raised to greatest integer of x over 2, this limit does not exist, because the right hand limit is not equal to left hand limit. So this is how we can solve these type of problems.